Introduction to functions. Points such as 2, 4 and minus 3, 2 are examples of ordered pairs. An ordered pair, denoted by x, y, is a pair of elements x and y in which x is considered to be the first element and y the second element. A set of ordered pairs such as a is equal to 1, 2, 2, 4, 3, 6, 4, 8 is called a relation. Every relation determines two sets. The set of all the first elements of the ordered pairs is called the domain. So all the yellow numbers, the first number in each couple or ordered pair, is known as the domain. The set of all the second elements of the ordered pairs is called the range. So the blue numbers are the range. Some relations may be defined by a rule relating elements in the domain to the corresponding elements in the range. In order to define the relation fully, we need to specify both the rule and the domain. For example, x, y, where y is equal to 2x plus 1, and x is an element of 1, 2, 3, and 4 is the relation 1, 3, 2, 5, 3, 7, 4, 9. The domain is the set 1, 2, 3, 4, and the range is the set 3, 5, 7, 9. The relation above may be represented by a mapping diagram as shown. So we have the domain highlighted in yellow and the range highlighted in blue, and we can see that 1 maps to 3, 2 maps to 5, 3 maps to 7, and 4 maps to 9. So if we take the final ordered pair that was given to us, so 4, 9, so 4 is the domain, and that maps to 9, the range. So we can see 4 maps to 9. Functions. Functions are special relations with individual properties. They are often referred to as number machines with inputs and outputs. When is a relation a function? A function is a relation for which each x value in an input set, there is a unique y value of an output set. When a function is represented by a mapping diagram, each element of the domain maps to one and only one element of the range. Consider these two mapping diagrams. So we have A maps to D, B maps to E, and B also maps to F, and then C maps to F. So this is not a function. It is a relation, but it is not a function. And the reason is that B maps to two different elements in the range. Our next mapping diagram, we have 1 maps to 1, 2 maps to 4, and minus 2 maps to 4. This is an example of a function because every element, so of all the yellow highlighted numbers, so 1, 2, and minus 2, so every element of the domain only has one arrow leaving it. So in our first example, that was not a function. We know that B, so A, B, and C are the domain. B had two arrows coming out of it, whereas in our example of a mapping diagram that is a function, we can see every element in the domain only has one arrow leaving it. I know that there is an element in the range that has two arrows going towards it, but that's totally fine. That's no problem. This function, for example, might be x squared. So 1 squared is 1, 2 squared is 4, and minus 2 squared is also 4. So this function might actually be the function y is equal to x squared. So it's okay for an element in the range to have two arrows going towards it, but you cannot have an element in the domain having two arrows leaving it. So diagram 1, so our first example, which is not a function, This is not a function since the element b is paired with two different elements in the range. So again, we can see b is being mapped to e, and b is also being mapped to f. So therefore, this cannot be a function. In diagram 2, so the one on the right that we decided is a function, diagram 2 is a function since each element in the domain is mapped onto one and one only element in the range. So each of the yellow numbers, so each of the elements in the domain has only one arrow leaving it. Remember, in the mapping of a function, only one arrow comes from each element of the domain. Each element of the domain is operated on by the function, i.e., there is an arrow out of every element in the domain. And just up at the top right-hand corner here, we have D maps to OR. So D stands for the domain and OR stands for the range. So the domain will map to the range. And this is just a handy way of remembering because you can mix them up easily. D comes before OR in the alphabet. So the domain is always on the left-hand side because the domain comes first, and then we have the range on the right-hand side. So just in case you were to mix up the D and the OR, the domain and the range, which is which, just remember that D comes before OR in the alphabet. So the D is first, the domain is first, and the range is second. So the domain is on the left of our mapping diagram, the range is on the right of our mapping diagram. Notation, domain, range. Consider this rule for a function. Square the output and add 6. If we input x, the output will be x squared plus 6. So we're squaring the output and adding 6. The rule for this function may be written in any of the three ways shown on the right. So we can say f of x is equal to x squared plus 6, or we can say f of x maps to x squared plus 6, or we can say y is equal to x squared plus 6. So f of x, and y all mean the exact same thing. When dealing with the domain and range of a function, it is important to know what the basic number systems are. These are given below. So capital N is equal to 1, 2, 3, the set of natural numbers, so positive whole numbers. So 0 is not included in that. Capital Z is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3, So the set of integers, so positive and negative whole numbers. So 0 is included in that. Q is equal to fractions, where A over B, A, B are elements of Z, and B is not equal to 0. So again, Z being an integer. This is the set of rational numbers. And then Q over or Q divided by or, is a set of irrational numbers. So some examples are pi, root 2, e. When all these numbers are combined, we get the set of real numbers, so capital or. Capital or stands for real numbers, and it's all the numbers on the number line. So positive, negative, whole numbers, decimals, fractions, irrational numbers, and so on. And or with a little plus is the set of positive real numbers. Consider the function f of n maps to n of x maps to x squared. This means that the set of input numbers comes from n, the set of natural numbers. The output numbers also comes from the set n. The set of possible output numbers is called the codomain. However, the outputs generated by the function f of n maps to n of x maps to x squared are the square numbers 1, 4, 9, 16, The set of actual outcomes of a function is called a range. The range is always a subset of the codomain, so a smaller set of the codomain. However, in some functions, the range and the codomain may be the same set. They may be just the exact same. The function f of n maps to n of x maps to x squared is shown on the right. The domain is equal to n, the natural number set. The codomain is equal to n, the natural number set. And the range is equal to 1, 4, 9, 16, So we can see on the left-hand side, we have the domain, and we have a capital N, which stands for the natural number set. So 1, 2, 3, 4, ... So the natural number set obviously is more than just 4 numbers, but there's just 4 shown in this mapping diagram. The function itself for the rule is x squared, and the codomain is the natural number set as well. But the range of this particular function is square numbers. So 1 squared is equal to 1. 1 times 1 is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So when you're given a function and you have 3 parts to it with 2 arrows in between, the first part, so to the left of the first arrow, so in this case it's f of n, so that represents the input. And in this particular function, the input is n, the natural number set. The middle part, in this case it's n of x, the middle part represents the output. And in this case, it's also the natural number set. And the last part on the right is the rule of the function. In this case, it's x squared. Now consider the function f of r maps to r of x maps to x squared plus 2. So again, you've got 3 parts and you've got 2 arrows. So the domain of f is the set of real numbers r. The codomain is also r, the real number set, so all numbers on the number line. Domain intervals. When we have an input, a function gives certainty about the output. To create functions from certain relations, it is necessary to restrict the domain and create intervals in which the relation is a function. When dealing with the log function, f of r, and we have a little plus sign, so that's the positive part of the real number line, the real number set. F of r, positive, maps to r of x, maps to ln x, so the natural log of x. The domain must be restricted to values of x values greater than 0. That is, x is an element of the positive real number set, because we cannot get the log of a negative number. For the function f of x is equal to root 4 minus x squared, the domain must exclude the values x is less than minus 2 or x is greater than 2, as these values for x result in the square root of a negative number, which is not a real number. Thus, the domain is x values greater than minus 2 but less than 2. So just to show, if we were to take a value outside of this domain, so greater than 2 is 3. So if we got f of 3, we would have the square root of 4 minus 3 to be squared. 3 squared is 9. So we'd have the square root of 4 minus 9, which would be the square root of minus 5. And you can't get the square root of a negative number. So that's why the domain has to be restricted to x values greater than minus 2, but less than 2. So 3 is obviously outside of that interval, so that's why 3 won't work. The main features of a function are highlighted below. So again, we have 3 parts. So in this example, we've f of r maps to r of x maps to x squared plus 2. So we have 3 parts with 2 arrows in between. So we have the name of the function, and then a colon, and then we have the domain, and that maps to the codomain, and a colon, and the input, so the x values, the input, and that maps to the rule of the function. So in this case, it's x squared plus 2. Vertical line test for a function. A very useful way to identify whether or not a relation is a function is to draw a graph of the relation and apply the vertical line test. If a vertical line can be drawn anywhere on the graph and it intersects the graph at most once, then the relation is a function. So for example, in this function, so the red curve is the function, x times x minus 3 to be squared. If we were to move this vertical line anywhere to the left or the right, it would intersect the graph once and only once. Whereas with the graph on the right, we have 2 points of intersection.